Imagine a world where instead of one giant AI assistant serving everyone through the same neural network, there are millions of persistent personal AI instances, each shaped by its own history with a specific user, yet all sharing the same massive foundation model underneath. That's the vision this paper from MindLab lays out, and the technical vehicle they propose is parameter efficient fine tuning, or PEFT, most famously embodied by low rank adaptation, or LoRA. Here's the intuition. When you interact with a large language model today, it doesn't really remember you across sessions in any deep behavioral sense. Long context windows help, retrieval augmented generation helps, user profiles help, but none of these change the model's actual behavior in a persistent, learned way. The authors argue that a small, trainable adapter sitting on top of a frozen shared foundation model can carry part of that persistent state. Things like your preferences, your tool habits, skills you've taught it, memory-like updates from repeated interaction. Think of it like the human genome. Any two humans share about 99.9% of their DNA, and yet that remaining 0.1% is enough to produce the full range of human individuality. The base model is the shared biology. The adapter is the tiny fraction of variation that makes your personal model yours. Prior approaches to personalization have leaned on retrieval systems, prompt engineering, or user profile documents fed into context. These work, but they're external to the model's actual weights, meaning the model itself doesn't learn or change. Full fine-tuning would change the model, but it's prohibitively expensive to do per user. LoRA has been around for a while as a cheaper alternative. But the paper's key reframing is that we should stop thinking of LoRA as merely a budget substitute for full fine-tuning and start thinking of it as a persistent unit of individuality that can be scaled to populations. To make this vision work, the authors identify three coupled scaling axes that all have to reinforce each other. The first is scale up, meaning the shared foundation model must be strong enough that a small local update actually has leverage. The second is scale down, meaning the adapter itself must be small, stable, and reliably trainable so you can afford to have millions of them. The third is scale out, meaning the infrastructure must support many persistent adapters coexisting, being served, evaluated, and composed. Miss any one axis, and the whole thing collapses. Strong priors without cheap adaptation stay static. Cheap adapters without strong priors produce shallow personalization. Both without infrastructure produces disposable variants, rather than durable personal models. Let's go deeper on scale up. The authors demonstrate that reinforcement learning on language models is fundamentally prior limited, meaning RL can only reinforce trajectories that the current policy already samples with reasonable probability. A stronger base model assigns more probability mass to useful but unstable reasoning behaviors, giving RL something to grab onto and stabilize. They then show that LoRA can be applied to a trillion-parameter mixture of experts model, specifically Kimi K2, using group relative policy optimization, and achieve stable reward improvements while using only about 10% of the compute of full parameter RL. But scaling up like this, exposes new failure modes that don't exist at smaller scales. The most subtle is what they call training-inference mismatch. In a mixture of experts model, rollouts are generated by an inference engine and gradients are computed by a training engine. And if tiny numerical differences cause tokens to be routed to different experts during training versus rollout, then you're optimizing a completely different computation than the one that produced your samples. Think of it like a chef tasting a dish, sending feedback to the kitchen, but the kitchen accidentally cooks a different recipe based on that feedback. Their fix, called router replay, or R3, records the routing decisions during rollout and replays them during training, keeping the KL divergence near zero and stabilizing gradients. Now scale down. The authors run a massive sweep of 216 runs across 9 LoRA ranks, 4 batch sizes, and 6 seeds. What they find is counterintuitive. Ranks 16 to 32 are the sweet spot for reliable deployment, but the truly interesting region is ranks 1 to 4. At rank 1, the best seed achieves performance comparable to rank 32, but the average across seeds is terrible and variance is huge. So the tiny adapter regime isn't under capacity, it's under optimized. The signal is there, we just can't reach it reliably. To fix this, they propose LoRA tail, a new initialization scheme. Standard singular value decomposition based initializations like PCA use the principal singular directions of the pre-trained weight matrix, but under reinforcement learning with verifiable rewards, this causes training collapse because those directions are exactly the most sensitive parts of the model, and updates there blow the KL budget that RL relies on. LoRA tail instead initializes the adapter using the minor singular vectors, the least dominant directions, which act as a safer optimization landscape. Here's the striking result. At rank 1, LoRA tail delivers a consistent 20% improvement over the base model across all batch sizes, while standard LoRA at rank 1 degrades catastrophically as batch size grows, going from plus 15% to minus 18%. On a 30 billion parameter mixture of experts model, LoRA tail beats standard LoRA by 11.5 percentage points, absolute at rank 1. They also tackle hyperparameter transfer across ranks, which becomes critical when you have millions of adapters and can't afford to sweep for each one. The question is, when you change rank because of memory constraints, how should you adjust the learning rate and the alpha scaling factor? Through careful early step analysis, they show that scaling alpha proportional to the square root of rank preserves the effective update magnitude across ranks, meaning you can reuse the same learning rate. This isn't a new theoretical result. It comes from earlier work on rank-stabilized LoRA, but they validate it in the harder reinforcement learning setting where the usable learning rate band is narrow and getting it wrong is costly. Finally, the paper gestures toward moving beyond static LoRA adapters entirely, introducing something called δ-mem, which maintains a compact online memory state that evolves as tokens are processed. Rather than being a fixed low-rank update, δ-mem reads from a previous memory state, generates corrections to attention, and writes updated information back using a delta rule learning update. This turns the adapter from a static parameter delta into a writable local state that accumulates history, which is much closer to what you'd actually want for a persistent personal model. Now for limitations. The trillion-scale LoRA-RL comparison isn't a clean controlled experiment. It varies model size and training method simultaneously, so it doesn't cleanly isolate whether the win comes from the stronger prior or the LoRA-specific properties. The authors acknowledge this. Also, the low-rank reliability problem isn't solved, it's just improved. LoRA tail makes rank 1 adaptation viable in the specific settings tested, but the broader question of when tiny adapters generalize remains open. And critically, the paper is quite honest that PEFT does not replace retrieval, does not store the whole person, and does not solve memory by itself. It provides a compact writable unit, not a full memory system. The infrastructure piece, called MeInt, is described more as a direction than a fully validated system. Now, let's walk through some questions you might have after hearing all of this. First, why exactly does reinforcement learning care so much about initialization when supervised fine-tuning seems much more forgiving? The reason is that RL updates operate under a trust region defined by KL divergence from the sampling policy. If your initialization biases early updates toward directions where small parameter changes cause large policy shifts, you blow the KL budget and the token-level surrogate objective breaks down because it relies on a first-order Taylor approximation that only holds when policies stay close. Supervised fine-tuning has dense token-level supervision anchored to fixed targets, so it can absorb aggressive early moves. RL cannot because its whole optimization framework is built on staying near the rollout policy. Second, if adapters are so small, why does the base model matter so much? Doesn't the adapter do the real learning? The adapter has limited expressive capacity by design, so it can't build new capabilities from nothing. What it can do is redirect and modulate capabilities that already exist in the base model. If the base model has never seen or approximated a useful reasoning pattern, the adapter has nothing to sharpen. The stronger the prior, the more latent structure exists for a small update to redirect, which is why a large model LoRA can outperform a smaller full fine-tune under the same budget. Third, what actually makes the routing replay trick work in mixture of experts models, and why isn't this a problem in dense models? In a dense model, every parameter processes every token, so numerical differences between training and inference stacks just cause small perturbations and activations, but the computation graph stays the same. In a mixture of experts model, a routing decision picks which experts a token goes through, and that decision is discrete. A tiny numerical difference can flip which experts fire, meaning training and inference literally execute different computations. Router replay solves this by recording the routing choices during rollout and forcing training to use the same choices, guaranteeing you're optimizing the same computation that generated your samples. So what does all this mean for large-scale recommendation systems, the kind that serve hundreds of millions or billions of users? The most direct application is user modeling. Today, recommendation systems represent users through embeddings learned in shared models, plus retrieval over user history. A per-user LoRA adapter, sitting on top of a strong foundation ranker or a generative retrieval model, could carry persistent behavioral state, things like a user's evolving taste, their tolerance for exploration versus exploitation, their session-level goals. The scale-down work is especially relevant here because at billion-user scale, even a few megabytes per adapter matters enormously, and the LoRA tail result suggests you could push down to rank 1 or rank 2 adapters if you get initialization right. The scale-out infrastructure question, how to store, serve, and update millions of adapters with low latency swapping at inference time, is exactly the operational challenge production recommendation systems already face with things like user embedding tables, just reframed as parameter space state instead of representation space state. Beyond user modeling, the trillion-scale MOE routing lesson is directly applicable to modern recommendation architectures that increasingly use sparse expert models. If you're doing online learning or reinforcement learning from user feedback on an MOE ranker, the training inference mismatch problem is going to bite you the same way, and router replay or similar techniques become necessary infrastructure. Finally, the diversity-based majority voting result, where combining outputs from different LoRA variants raised accuracy substantially. Hints at ensemble strategies for candidate generation, using population diversity across personalized adapters as a resource rather than a nuisance to be averaged away.